this W is your affinity, and you have calculated it, and so it is ready for good clustering. So you can use the theory of spectral clustering in graph theory in order to do clustering. And so the sparse subspace clustering, first we calculated C, and second we calculated C plus C transpose, and finally using spectral clustering and apply spectral clustering to W in order to segment it. So what makes a good cluster? So we divide the vertices into A and B. For example, this is 1, this is 2, this is 3. And we have another group cluster, which is 5, 4, and 6. So we want to, and of course they have some weak connections. And now I do a cut. So this is A, this is B, which is equal to vertices in this graph except A. So we have a graph G having vertices and edges. And we want to maximize, so the goal is to maximize the number of within cluster connections, and we want to, on the other hand, we want to minimize the number of between. For example, here we have only 2 edges. One edge is this one, the other one is edge this one. So we want to minimize these edges between connections, between cluster connections. So back into subspace clustering, you see that different points lies on different subspaces. For example, here, we want to say that this clustering is bad because we have another subspace that only 2 points lies on that. So it's a bad one. So it's like you have a very complicated graph, and it is only, this is black one, this is black cluster. So it is only related to this via 2 edges. It is very good, but the inside this cluster has only 2 points, which does not maximize the within cluster connections. And you see how subspace clustering is related to graph partitioning. I mean, the geometric intuition is very interesting. If you get this, then you have the motivation to develop more theories on subspace clustering. And now our affinity is just C plus C transpose. As I said, C is calculated using ADMM n times, and this is what makes a good cluster. Now let's talk about graph cuts. Cut, I mean by cut, it means the set of edges with only one node in the cluster. So cut of A is sum of Wij, which is I is in A, but J is not in A. So it's like we have 3 nodes in this cluster. This is A, and we have 5, 4, 6 This is cluster B, for example, and this is so cut of A is 2 because there are two edges that relates cluster A to cluster B. So we want to express cluster quality as a function of the edge cut of the cluster. The degenerate example is that you have a nice connected graph, and then you only have one point in the other graph. And then when you cut that, so it's not a good partitioning. So let's modify our cut score in order to handle these kind of outliers. This is outlier, you know. In order to handle this outlier, we define the concept of conductance. So the concept of cut of A was good. Now we want to say that if we just define the conductance by 2m minus volume of A, and you know the volume of A is the total weight of edge with at least one endpoint in A. So this is volume of A, which is the sum of your degrees. This is exactly the sum of degrees. So di is degree of node I. So the conductance or phi of A is this. And we divide by this because, you know, the size of A is less than the number of vertices. Divide by 2 to compensate this in order to avoid this from getting too large. And so let's talk about graph Laplacian matrix. But before talking about graph Laplacian matrix, let's remind you about adjacency matrix W, which I said we write it as this. So we have this matrix, and some of them are well connected. So it means that node J is connected to node I here. Node J is connected to node I. It means that you have a graph here, and you have a graph here, and two of them, for example, is connected. This is your cut. And so this is the red cluster, and this is the blue cluster. Blue cluster is fully connected to itself. Red cluster is fully connected to itself. And we have some interactions, but very, very few interactions. So the task, so W is the adjacency matrix. So the task is to partition the graph into pieces such that the resulting pieces have low conductance. And in adjacency, let's say Aij is 1 if I and J is an edge. If Aij is 0, then it is not an edge. And let's say that X is a vector of labels or you might say, values of each node of G. I want to say what is the meaning of AX? What is the meaning of AX? So yi is j from 1 to n, aij xj, xj, I and j inside E. So A11, A1n, AN1, ANN times x1, xn, this is x, this is A, is equal to y1 through yn. And if this is node I, all of them, for example, 1, 2, and the jth one is here. So the jth, so when I say AX is equal to, when I say AX, it means that the sum over all xj. So it has a meaning if I and j are an edge. So what is the meaning of AX is equal to lambda x? You know, in spectral graph theory, the idea is to analyze the spectrum of this adjacency or Laplacian, which is d minus a. So Laplacian is d minus adjacency. To analyze this spectrum, I mean, what are the eigenvalues, what are the eigenvectors, and to sort them somehow to something like this. And for Laplacian, you will see that this is 0 and we care only about the second. Of course, there are theories on how the rest of the eigenvalues could be useful. So let's suppose that we have a d-regular graph. What does it mean? It means that all nodes in G, all nodes have degree d. Degree is equal to d. And G is connected. So this is the meaning of the regular graph. So what is the meaning of AX is equal to lambda x? Let's try this 1, 1, 1. Maybe this becomes an eigenvector, who knows? AX is d, d, d. Oh, it's like saying that d is the eigenvalue of A, and x is the eigenvector. So it has a nice meaning. Now, suppose that G is not connected. If it is not connected, and for example, G is like this, A and B is this. So G has two components and each of them is d-regular. So put all 1 on A and 0 on B. So define x prime is 1 on all of the A and 0 on B. So it turns out that AX prime is equal to D, D, and the rest of them are just 0. Same for X when the first entries are 0 and the rest are 0. So AX is equal to, now the first entries are 0 and the rest are D. So in both cases, you see that lambda is equal to D. Of course, we are doing it for this affinity adjacency matrix, and if you do it for Laplacian, you see that all of them become 0. So the intuition behind that is that if we have A and B partitions, then lambda 1 is equal to lambda 2 if those two graphs are not connected. But if they are weakly connected, then lambda 1 should be around lambda 2. So the first and the second eigenvalues should be almost the same things. So this is just the intuition. And I don't say any rigorous mathematical things about that yet. So the adjacency matrix, first of all, adjacency matrix is symmetric. Secondly, the eigenvectors are real and orthogonal. So let's define the degree matrix. Degree matrix. So L Laplacian. Of course, I have talked about this several times, and you know that this is the degree, this is the adjacency. For example, let's say -2, -1, 2, -1, and sum is 3. So the trivial eigenpair is x is 1, 1, and Lx is 0, and so lambda, the eigenvalue, is 0. You understand that this is the trivial eigenvector and this is the trivial eigenvalue. So each row, as you see, each row sums to 0. And each columns of L also sums to 0. Each column also sums to 0. And the eigenvectors are real and orthonormal eigenvalues and non-negative. So eigenvalues are non-negative. It means it is greater than 0 for real numbers. So let's talk about the meaning of lambda 2. We want to partition using graph Laplacian. So when we want to minimize, first of all, you can calculate. You can show by just doing the Lagrangian multiplier that minimum of x transpose mx over x transpose x, and this is the second smallest eigenvalue. So what is the meaning of x transpose Lx? For example, M is L. What is the meaning of that? You can write this as Lij xi xj, and from the definition of the Laplacian, you can write this as Dij minus Aij xi xj, and since D is diagonal, you can write it as Dii xi2 minus Ij 2 xi xj. Why? Because recall that sigma Aij xj is just the sum of your labels. Of course, if I and j is an edge. And using the definition of D, you can write this as xi squared plus xj squared minus 2 xi xj. I and j is an edge. So this one, this is the square of xi minus j squared, I and j e, and